So what I want to do here is come up with a formula for the volume of something called a frustrum. Right? A frustum of a cone is it's a cone with the top part chopped off, right? And it's chopped off in such a way that the two bases, the previous base plus the new base up there at the top, are parallel to each other. So to do this, I need to kind of get a coordinate system going here. So I'm going to drop one axis down there through the centers, right, perpendicular to the bases. You can think of this one as being the y-axis, right? The x-axis is going to run through that radius of the lower base. And now you can kind of see the parallel, the trapezoid there that we're going to rotate to make the frustrum. So to do that, first thing I have to do is I have to come up with an equation for that boundary line, right? That's the edge of the frustrum, what was the edge of the cone. So to do that, I need 2 points, right? The lower point there is going to be capital R comma 0. The upper point is going to be lowercase r comma h. From that, I can calculate the slope, right? You're going to use the slope formula. We get that that's negative h over capital R minus lowercase r. Then I'm going to use the point slope formula to come up with the equation for that edge, right? And I'm going to use the bottom point, r comma 0, to do that. So if we substitute into the point slope formula, we get this equation here. Now, what do we want to solve this for? Well, we're rotating around the y-axis. Remember, it's kind of a reversal because I'm going to rotate around the y-axis. I'm going to take this equation and I'm going to solve it for x, right? And if I do that, I won't bore you with the algebra here. We get this equation. And if we use the disk method, that's going to be the radius of our individual disks. So now we can go to the formula, right? Remember, the formula is volume equals pi integral r squared dx. So if I substitute our x equation here for the radius and our boundaries, think about where we're going to and from on that y-axis. We're going from the origin, which is y equals 0, and we're going all the way up the height of the frustrum. So we're going to go from 0 up to h. Okay, that really was the hardest part of this whole thing. That expression there, I know it looks kind of messy. It's got all sorts of multiple variables in it and so forth. But ultimately, that's just a polynomial, right? So we're going to integrate this using the power rule, do some substitution. We should come up with our answer, right? So let me rewrite this, right? There's our formula. So what I'm going to do is I'm going to start by multiplying out that square part in the integrand, right? And that's going to give me capital R minus little r over h squared y squared, right? That's the first term squared, minus 2 times the product of these two terms, capital R times capital R minus little r times y over h, plus, then we square the last term, that's r squared. Now remember, we're integrating this with respect to y. That means everything else, all those r's and h's, those are just constants, right? So I'm going to apply my power rule to the y squared, the y, and the constant term. And if I do that, the y squared becomes y cubed over 3. The y becomes y squared over 2, but I canceled that 2 with a 2 that was already up there in the numerator. And the r squared term becomes r squared y. Of course, we still got that pi floating around out in front. Don't lose track of that. And now we're going to evaluate this from 0 to h. Well, hopefully you can see pretty quickly when we put 0 in there, everything is going to become 0. So really, it's substituting h that's kind of going to give us the result. So if we put h in there, we get this expression. All I did is replace all 3 y's with an h. And really, that is kind of the answer, but obviously we're not going to stop there. We do need to do some simplifying. So what I'm going to do is, in the first term, that's going to be an h squared in the numerator and an h cubed, an h squared in the denominator and an h cubed in the numerator. Those are going to cancel and leave me with just an h times everything else that was in there. Capital R minus little r squared over 3. And see, we're going to get cancellation here in the middle term as well. That h squared and the h are going to cancel and again leave a single h. Right? The fraction is now gone. And there's nothing I can simplify there in the last term. Now, that was actually really nice, right? Because now every term has an h. All right, so let's factor that h out. And I'm going to factor the fraction out. Right? I'm going to factor out h over 3. Right? So that's why I'm left with these two 3's that you see on the second and third terms here. Okay, now it really is just kind of a little bit of an algebra problem. Multiply all of that out. The first term becomes capital R squared minus 2 r times r, the two r's, plus r squared. I'm going to distribute the minus 3 capital R into the parentheses. And now is when the really cool stuff happens. I've got a 3r squared minus 3r squared. Those go away. I've got a minus 2 product of the r's plus 3 product of the r's. Those are like terms that I can combine. And if you do that, all that's left is this. H pi over 3 times lower radius squared plus the product of the radii plus the upper or the smaller radius squared. And that's our formula. Right? That's the formula for the volume of a frustum. Okay. I picked this problem for a reason, for us to look at. Really kind of the interesting part, I think, was coming up with that linear equation for the boundary, and then knowing what to do with it, knowing to solve it for x instead of solving it for y. Okay, beyond that, it was really very straightforward integral, but it was kind of a messy integral, right? And if I'm being honest with you, in my opinion, there really was an easier way to do this if you remember some of your high school Euclidean geometry. What I've done here is I've filled in kind of that part of the cone that we cut off. If you take the area of the big cone, subtract out the area of the little cone, you've got the area of the frustum. And using some similar triangles, we could figure out the area of that upper cone pretty easily. So like I said, I picked this question not because this was the best way to do it, but because I thought it illustrated a useful technique for this kind of problem. But really, kind of the takeaway here is don't forget everything you've learned so far. You know, yeah, you've got these great shiny new calculus tools in your toolbox, but they're not always the best way just because they're the fancier way. Right? So keep those older kind of classical geometry methods in mind here as well. So there's some links here if you'd like to see the lecture where I discuss the disk method. Right, there's a link to it there. And if you like this example, please don't forget to click on the like button down below as well.